Good afternoon. So we're continuing talking about memory safety, if you remember. Just a couple of announcements. One is I think next Monday is a holiday, so no class. So that our next presentation would be on next Wednesday. So just be and we're gonna basically move to Wednesdays, starting next week for the presentations. Uh, your next CA, as I said, is available online, and the next one, which doesn't, have that much interest in people that I upload both of them at the same time, but you can take a look at both. Today I'm going to explain a little bit of what you need to do on CA3. So later part of the class is actually mostly about your project. And then next week's lecture is going to help you with the fourth project as well. Which we probably, if we finish early today, I'm going to start a little bit of that today as well. Let's see how we move forward. Does anybody have any questions? Good. All right. So if you remember, we were talking about memory corruption, right? And it said that essentially the problem with memory corruption is one way or another, the attacker can corrupt something in the memory. There are many examples of this, including various different type of invalid dereferencing, which could be either temporal, spatial. There are many others as well, such as integer overflow, heap stacking, spraying, things like that as well. And generally what will happen is that there's kind of this timeline that happens when we are attacking a system, which, the attacker corrupts the memory. This corruption could be either the code or data, it could be the location, or it could be the pointer itself. And then the attacker could optionally use the corrupted value. If the attacker actually used the corrupted value, then they can actually do much more sophisticated attacks, including control flow integrity or control flow hijacking attacks that we started talking about. Example of that was buffer overflow. Essentially, the way that buffer overflow works is that it's kind of exploiting this notion in systems that we have a calling convention, which we kind of need to change the PC when we are jumping and jumping back, right? So when we are moving from one function to another function, we need to use and change the PC. And then the stack would look like something like this that we described, different things, function parameters. The most important thing is the return address and the pointer, and then of course a bunch of space for local variables. Here I'm just giving you example of 20 bits, but this is just any arbitrary size buffer, right? So what will happen is that the attacker can essentially do overwriting by creating some kind of corruption in this buffer, right? So again, the source of the corruption could be anything, could be some form of dereferencing, could be anything else, depending on the language, depending on the data, depending on the system that's being attacked. But the problem is that there are many of these potential corruption possibilities, and as a result, being able to overwrite memory is not that hard problem. Of course, there are lots of research on programming languages, on compilers, on software engineering, and so on in order to kind of fix these issues. But this is something that's out of scope of this class of like how do you actually write good codes that doesn't have those problems. But for those of you who are interested more at the higher level, like software level stuff, that's an interesting and important area of research. So anyway, the attacker, one way or another, tries to kind of overwrite this return address. What will happen is that essentially this return address could cause the system to jump into any arbitrary program. All the attacker needs to do is that instead of writing arbitrary stuff to that buffer and corrupting arbitrary part of memory, they actually engineer it exactly such that this point that's being corrupted is having this value that points to another part of the memory, such that once the return instruction is being executed, instead of jumping back to the main memory, to the main function, which it's supposed to be here, now it's jumping back and it's jumping to some arbitrary part of the memory, right? And then essentially we are hijacking the control flow of our system, allowing the adversary to just essentially run arbitrary instructions. And of course, if the attacker gets access to running anything like arbitrary things here, you are essentially giving them unlimited access. In other words, the attacker can now, after this function, run another function, another function, another function. Because like if you can do it once, then you can essentially just fill the stack with all the addresses that you want. So each time you return, you jump back to another function that the adversary wants, another function that the adversary wants, and so on. So could forever the adversary can take control of the system, really, until, of course, the system reboots. So then we kind of talked about, oh, okay, if you're jumping to anywhere, where should we jump? And I told you that, again, this is also part of the research that there are many people worked on. There are many different solutions. The most popular one is what is called shellcode, which essentially this kind of very few line of codes that cause a shell to be invoked. And then the good thing about shell is kind of this mother of all these other attacks kind of things, because as once you have the shell, you can run any arbitrary binary file, right? So that's the main motivation of running and opening a shell rather than really executing, but nothing prevents you to run any arbitrary code that you want instead of having a shell. So this is kind of the algorithm. That's kind of like, of course, it's not applicable to any program. It's not like, all of your programs are vulnerable to this. Your program has to have a particular vulnerability. If it doesn't, if you use like a, type safe, language, or your system is being protected, then you're not vulnerable to this attack. So it's not like, oh, every single program that we write is potentially vulnerable to this. But if it is vulnerable, then the attacker can find it and write the malicious code and so on and so forth. Another way of running this shell code is injecting it with the code itself. So a little bit of more engineering was that if I'm kind of like writing things and engineering that this return address would be the return address that I want, what I can do is that instead of like, basically overwriting this middle part with arbitrary values, I actually kind of overwrite this part with good code that I want to, right? So I will basically overwrite this part with my shell code. And optimization that I described was that the problem with the shell code is that it needs to be very accurate, because think about it as a program, but this needs to start exactly at the beginning. If you start a program from the middle, it's not going to work, right? So we need to know exactly where shellcode starts, and that's a problem. That's kind of like an extra engineering effort required. As a result, it's kind of like this common optimization is to kind of have a landing area that you kind of pad your shellcode with a bunch of no ops at the beginning, and then have the actual code here. And the idea is that anywhere here will do, right? Because it doesn't matter where I land. Wherever I start my no ops, then I eventually gets to my real code. And this is something that's being used most commonly. Then we also talked about what if we cannot really execute anything on the stack. In other words, if I even inject my code, I cannot really execute it, because a common defense solution in these systems is making the stack non-executable. And then solution for that, again, is also very popular type of attacks, and that is what we call code reuse attacks, which the idea is that we don't really inject malicious code, we just use existing code in the system and try to kind of reuse it for our own malicious purposes. The first one was returning to libc kind of attacks, which essentially one can use libc or any other libraries in the system and find kind of gadgets in that libc that creates kind of interesting attacks. And the reason that libc particularly has been chosen is that libc exists in mostly all the systems. It's a huge amount of code base, so there are lots of things that one can use. Particularly, people have found that one can launch shell code using just libc code. A more generic type of return to libc is generally what we call a return-oriented programming, which essentially what you do is that you search for these gadgets in your memory, and gadget is essentially a sequence of instruction that ends with the return. So anything that's like a sequence of one or more than one instruction that ends with the return, we call it a gadget. What we do then is we essentially run these gadgets one after another. In other words, we're kind of creating this notion of like a big program by just running few instruction, return few instruction, return few instruction, return, and then we can kind of stitch them together in order to create a program. This is what we call a ROP, or return-oriented programming. There's also jump-oriented programming and data-oriented programming as well. These are kind of like, other variants of return-oriented programming. A few of them people are going to discuss next week when they're presenting their papers. If you're more interested, you can always also look into return-oriented programming yourself. This is one paper that you may want to take a look at. ROP is still dangerous. But return-oriented programming is actually the concept that's kind of introduced in 2009, 2010. That's that time frame, and for like 5 to 10 years, it was like very powerful. These days, it's less popular because it's kind of like a very saturated area, but still there are lots of attacks using return-oriented programming. And then generally, how common is this? This is actually the most concern in security systems. Because there are many, many unsafe languages and bugs and functions. And most of the software, unfortunately, we have are vulnerable to one way or another to these type of attacks. Then at the last point of lecture last time, we start talking about defenses. And we kind of give you a few different options. The first one, of course, is kind of like fixing the problem, the root cause of the problem, and that was the unsafe languages. So if you actually don't write unsafe code, or kind of like have a mechanism to at least detect it or remove it, or altogether just not use unsafe languages, then of course you are secure against this type of code injection, memory corruption, attacks. You can also, instead of like doing it at the software or the programming language level, you can do it at the compiler level. There are compiler defense mechanisms that kind of try to detect this and add proper checks. The operating system technically can do this for you at some point. But then we are also start talking about kind of like more of a hardware level solutions. The first one was the stack canary or stack protection. The idea of stack canary was like your stack could be like, we can add an additional entry to your stack, which we call a canary. The idea of the canary was like we put it in the middle between the return address and the local variables, such that if the return address is going to be overwritten, it is guaranteed that the canary has been also overwritten. So now the idea is that if I can check the canary and make sure that the canary has not been overwritten, it's guaranteed that the return address has not been overwritten, right? So this would be one way of checking this. Of course, this comes with its own overheads, because now we need to kind of have a mechanism to check the canary each time that we are doing a return. We need to do a mechanism for generating this canary values and so on and so forth. So there's additional things that needs to be done that many systems doesn't have that. A similar way to stack canary is what we call shadow stacks. The idea of shadow stacks are also pretty similar to stack canaries. The difference is the shadow stack is kind of like thinking about this as a replicate of your stack, where you put your return addresses and your more secure, more sensitive values there, or at least you have a copy of your stack all the time on your shadow stack. And what you would do is that you always, whenever you want to return, you compare your shadow stack with the original stack. If they are matching, then it means that it hasn't been overwritten. Because the idea of shadow stack is that its shadow stack is completely hidden from the user. So the user cannot overwrite things on the shadow stack. They can overwrite things on the stack. Okay. So the shadow stack is just a pure hardware solution that just whatever you do on the stack, it just directly copied in the shadow stack and so on. Okay. And then there are attacks to both stack canaries and shadow stacks. So they have their own problems. And as I said, there are two problems. One is there are attacks for them, and the second problem is that they come with like overheads, including the performance overhead or area overheads. Then we also talk about other things, such as execution prevention, which means that this is like a simple fix that as I said, this is standard these days. And the idea here is that we want to make sure that not all the part of the memory is executable. The idea for this is that if somebody managed to inject something, even if they successfully inject things, if you make that part of the memory non-executable, then the code cannot be executed from there, right? So, for example, a common thing that we do is that we make the stack non-executable. And another thing that we usually do is like, executable and write together, which means that if something is writable, should not be executable. If it's executable, should not be writable. If we kind of combine these two together, then we kind of like make sure that our system is secure, because if something can be written, which means that potentially the adversary can write to it, so we can make sure that it's secure by making it non-executable. On the other hand, if you really need to write it, then if you really need to execute it, then we have to make it read-only. The problem is that there are some pages that you need to have both executable and writable together, like, for example, self-modifying codes and so on. So those are actually parts that the adversary can still exploit. But in most systems, you usually make sure that this property exists, that your code is your pages or your memories regions and so on, either executable or writable, not both. Then we also talk about ASLR. The idea of ASLR was that, we make it harder for the adversary to kind of predict where the addresses are. This includes where the return address is, where the return address points to, make it more difficult for the adversary, for example, to find the gadgets, and all those things. So essentially all of those kind of like attacks that we talked about, ASLR makes it much, much harder for the adversary to find those, right? And there are works to show that, if there are enough randomization and so on, then the adversary has this much difficulty and so on. But of course, ASLR doesn't completely eliminate the chance of attacks. There are still, again, techniques that tries to kind of circumvent ASLR one way or another, and then try to attack the system based on that. But again, ASLR is something that's commonly used in modern systems. It's just common practice to use ASLR. The last thing that we're going to actually talk more about in the next module is control flow integrity. The idea of control flow integrity is this, that if I know what is my control flow path, then I can enforce this, right? I can check this and find illegal transfer. So what is a control flow? That's something that I'm going to actually discuss further today. But essentially, think about your program as kind of sequence of instructions. Then usually some form of branches, right? Some if then else's, while loop functions, things like that. And then you kind of like based on the path, you kind of run some other instruction. Then there is another usually sequence and so on and so forth. And then at some point they might actually converge to something and so on and so forth. So this is what we usually call basic blocks. So this kind of sequence of instructions that not being interrupted by anything, we call it basic blocks. Again, later I'm going to actually just explain this more formally. But essentially, when we have basic blocks, then we have what we call a control flow path, which means that what is the sequence of basic blocks that I'm executing. So for example, the path in this particular example could be something like I'm running this, then running this, and then running this, and maybe then running this, right? So this is the path. This is from the beginning, the first instruction that I'm executing all the way to the last instruction in this function. This is the path I'm taking. If I change the inputs, I might follow the same path. I might go into the different path and so on and so forth. The reason that you might have different paths is that these conditions is usually data-dependent conditions, right? So for example, if x is less than 3 or f is greater than 3, do this or do that. So depending on these values, you might have different path, and as a result, your control flow changes, right? The idea of control flow integrity, though, is that you can predict what are the kind of valid transitions, right? So for example, in this particular scenario, you know that from this particular basic block, you can either go to this basic block or this basic block, right? So let's call them, let's put the number for them. For example, this is 1, this is 2, this is 3, okay? So from 1, I know that there's only 2 possibilities. Either I have to take this path or this path. There is no third, right? So the idea here is this, that whenever I kind of like, and now consider this as kind of like a call function. Like whenever I'm calling, I only need to, I can only just go here, right? So this means that I can basically know what this instruction, what's the address of this instruction is. Okay, and what's the address of this instruction is. In other words, I know what are the valid values for PC should be, right? So whenever I see this, the PC has to be changed either to beginning of this basic block or beginning of this basic block. So there are two valid values for PC. If I see there is something else during this execution, I can quickly kind of detect that there's something going on. Remember, in the attack that I described in buffer overflow, the problem was that the attacker can actually jump into some random. So from here, basically, my control flow says that I have to go back here. Okay, so there is one valid transition from one PC value to another PC value. But the attack, what happens is that it's jumping to somewhere else. So the PC gets some other value, right? The value that we haven't seen before, the value that is not part of the valid sequence of PCs. So if I can detect these transitions, right? If I can detect the transition of my PC, and if I can kind of validate whether this transition is a valid transition or not, then I technically can say whether the buffer overflow is happening or not. Then I can prevent, right? So I can, the moment that I see an invalid transition, then I can, for example, reset the system, stop the system from being executed, and so on and so forth, right? So the basic idea here is that I need to know a sequence of valid transitions, and then I need to basically be able to detect and prevent that from happening. Of course, the problem with control flow integrity is this detecting all this legal transfer is not something simple. For a simple example like this, that you have like an if then else, then that's very simple. You know that there are two possibilities and then you're good to go. But consider these kind of like indirect jumps, right? Something that can essentially takes any value. So based on the value, like think about a case statement or generally like these kind of functions that based on the value, they can jump to any of these functions. Since they have like, a number of different possibilities, then enforcing and finding all these legal transition is not something simple that can be done. For if and else's for like 0 or 1 is simple, but for indirect jumpers and generally indirect branches, this is not something simple that can be done. Still doable. So I mean, control flow integrity is a valid solution in most cases, but it's not as easy because now you need to kind of traverse through all the possibilities and extract all the valid transitions and so on and so forth. And it comes with extra overhead because now you need to do this in runtime, right? So you need to, for every single branch, you need to check whether this is the valid branch or not. And this adds additional, additional delay to your system. Okay? But we're going to talk about this control flow integrity a little bit more once we're finishing this discussion today. Questions so far? All right, so let's talk a little bit more about kind of like these vulnerabilities. I told you that one thing that we want to do is being able to kind of either prevent or detect the presence of this memory vulnerabilities. Okay, so one thing I can do is that for a given program, I can try to check whether I find any potential vulnerability in the system. Okay, for example, if I want to see whether, for example, this particular part leaks or not, or whether if I want to kind of extract all the possible control flow, possibilities in this program or not, I need to analyze this program in order to find this different path, right? So for this, we usually use these different tools. The main thing that we do is using what we call static tools. Example of that was, for example, antiviruses that I described for malware detection. If you remember, the idea in malware detection was that we are looking for specific patterns in the system, and we use antiviruses to kind of scan and find those patterns. So the same idea applies here when we are talking about this binary attacks. The idea is that can I find those specific patterns? Okay. Another solution that we do for static tools is what we call attestation. I'm going to talk and come back to this once I'm finished this. So this would be the second module. Very briefly, the idea of attestation is trying to kind of checking the current status of the code and making sure that the code is the same thing that we think it was. But what I want to talk about now is, can I use this sort of analysis engines to find specific patterns in my system, such that if I find those patterns, say that, okay, this system is, for example, vulnerable to buffer overflow, or vulnerable to ROP, and so on and so forth. Okay. There are various ways of doing this. There are, generally binary analysis tools, and then there's also what we call symbolic execution tools. Static tools is essentially what they do is that they're investigating code for a specific bug. Okay. The interesting thing about this is that it's not bugs, it's not necessarily security bugs. Our main focus in this class is finding these particular patterns that could cause memory corruption attacks. But essentially, static tools are also very commonly used when you're testing your system. So if you're doing any sort of software engineering, you want to make sure that your system is working correctly. You use the static tools to make sure that it's actually the control flow is following the same way that you think it follows. Typically, in order to kind of achieve this static tools, you use a bunch of different rules. So you define some set of rules, you follow those rules, and then you kind of like analyze your system. This is actually what we want to do in your kind of project as well, in your computer assignments this week. For example, let's say the examples that we are looking at is something like, if you're finding any unbounded writes, right? So for example, if you find some form of like, there is a pointer that, it's being written outside the bands. For example, it's defined as 0 to 40, and somebody's trying to write at the index 42. Can I find something like this? And then maybe the rule would be that if I see this, I print a message or record it somewhere, things like that, right? So the idea here is that your tool is essentially go line by line in your code, try to kind of check some specific rules. For example, in this particular case, it has to kind of know what is the size of the array and what is the current index of the array, and kind of combine, compare these two. And then based on that, decide whether this is a violation of that kind of rule or not. The biggest problem with static tools is scalability. The problem with this is, there could be many different paths in the program, right? And statically finding all those paths is not something very simple because, consider just something like a for loop. Essentially, a for loop is something like this, right? It has a baggage that goes back to earlier stages. And then you can easily get into this loop of like many different possibilities. So it has this important issue, which we call scalability, that how we can actually kind of have a good coverage of the entire program without really kind of running into the scalability issues. So this is, as I said, this is generally what we call a coverage issue, that checking whether or not a particular instruction is problematic is not that difficult. But checking all the instructions is a very big problem because there are many different solutions. So an alternative to this is essentially what we can do at the dynamic level, which the idea is that let the program kind of runs, right? And as it runs, then you can kind of follow the path, and then you will know what is the path that's been taken. It has its own challenges that I'm going to describe. Similarly, it has the coverage issue because now you need to make sure that the input has kind of exhaust all the different paths, and then we're going to talk about a solution for it. But the good thing about the dynamic tool is that it addresses many of the challenges in the static tool, because now you don't need to kind of keep track of every possible path at every time. You just follow the path that's kind of being executed at the current moment with the current input. So an example of this is Intel Pen tools that we're going to describe shortly. Before that, let's actually talk about a quick background of like this control flow path and basic blocks and these things. This is actually what you're going to use in your project as well. So first of all, why do we kind of like use this? This is, by the way, kind of borrowed from my colleague at Georgia Tech. So we be using this kind of software abstractions, things like basic blocks, or control flow graph or data flow graph. These are abstractions that we make. These are not real things, right? These are abstractions that we make in order for us to kind of understand what the hardware does, what the software does, okay? So for example, programs are written in many different languages. They have thousands of millions of lines. They have many other dependencies and so on. And then if this is at the source code level, if you look at the binary level, this is even worse. There are many different platforms. It's not human readable and so on and so forth. So what we need to do is kind of creating some form of understandable model of the software. And this is usually what we do with like creating what we call basic blocks and control flow graphs, okay? So what we do is kind of like things that we do is like we create things like basic blocks, we create things like control flow graph, data flow graph, program dependent, super control flow graph, call graph, and so on and so forth. I'm going to mainly talk about these first two, but there are many of these other analysis that is commonly being applied when we're talking about the software representations. If you're interested, definitely take a look at those as well. So what is a basic block? So the formal definition of basic block is that it's a sequence of consecutive statements. Usually when we're saying statements in this class, we mean the actual ISA instructions. The main thing about the basic block is that it has a single entry point and it has a single exit point. Okay, so it's a continuous sequence of instructions that starts at some point and exits at some point. So, which means that you cannot really, enter in the middle. You can only enter at the entry point and you can exit at the exit point. Okay. So in other words, the control always enters at the entry and exits at the exit point. There is no possibility of exiting or halting anywhere in the middle of the basic block. And then, if your basic block is just single instruction, then that means that your entry and exit are exactly that one single statement, that one single instruction. So it's totally normal for a basic block to just be one instruction. In fact, the examples that we're going to go through, there are like ones that has only one instruction, but the whole point of a basic block is that it has to be continuous. Okay. But continuous could be also means one. So let's actually go through this example, and this is actually what we want to kind of create in your project as well. So this is like a simple C code that's kind of do some form of like trying to kind of actually computes the power exponent function. So what it does is that it has kind of two local variables, the power and z, and it takes two inputs, x and y. If y is less than 0, then power would be equal to negative y. Otherwise, power and y is the same thing. Then z is equal to 1. And then what we do is that we kind of first multiply x to itself, and then continuously kind of doing this over and over. Essentially, this is the concept of like, 2 x to the power of y, right? So you kind of multiply x, y times to itself such that you get x to the y computation. If it's a negative number, then it's kind of a division kind of equivalent of that, right? So that's a simple thing, as you can see. Interesting thing here is that you will see that there are kind of different paths, right? So you essentially start from here. The first thing you will see is this kind of instruction here. And then this is one control flow, because based on the value of y, you either run this instruction or run this instruction, right? So you see that there is kind of two possibilities because of this control flow. And depending on the value of y, sometimes you run this and sometimes you run this, right? So you see that there are two different possibilities here. Similarly, when we are kind of executing this while instruction, you will see that the number of times that we kind of run these, two instructions depends on the value of power. If power is 2, then you do it 2 times. If power is 5, you do it 5 times, and so on and so forth. So it's kind of like, again, it's a basic block that also has a backage because it goes back to the top part of itself. And then finally, you have another if statement that if you need to do this, you just, kind of like, divide it, kind of invert it, and then finally you return it. So if you actually think about the blocks, you will see that, you have this different basic blocks here. So the first basic block that you will see is basic block number 1, and it includes lines 2, 3, 4, and beginning of 5. Okay. So first of all, like the first line is really not an instruction; it's just a definition of a function. And 2 and 3, 4 and 5, these are all just instructions that kind of defines local parameters. These are like push and pops in the stack and so on. So if you actually if you were to look at the assembly version of this C function, you will see that basically what these two kind of line of code translated to is kind of like pushing stack down because you want to create spaces for your local variables. Then you eventually reach into this kind of condition, and that's where your basic block ends, because now at this point you can either go left or you can go right. So this is where your kind of exit point is here. And then of course your entry point is line number 1. This is where this basic block particularly starts, because that's where the function is being called, right? Then you have the second block, and the second block is just instruction 6, right? So the instruction 6 is essentially just the entry and exit point, as I said, is exactly this, just this one instruction, because if this instruction executed, then we have to jump over 7 and 8 and then do 9. If this is not executed, then we have to do 7 and 8. And then similarly, if you follow, we will see that, for example, the next basic block is 8. This is just this instruction, and then the next basic block is just 9. You see that actually many of the basic blocks are just one instruction. Then we will see that 10 is a separate basic block. The reason that 9 and 10 is not together is, remember that basic blocks should have only one entry point. Okay, so in this particular case, 9 is your entry point. But if 10 were also your entry point, then at some point you need to go back to 10, right? Because this is a while loop that needs to be continuously executed. So from 12, you had to go back to 10, which is not possible, because in that case, then you would have 2 entry points to this basic block, both 9 and 10. As a result, you kind of make 9 and 10 as 2 separate basic blocks. So 9 is a separate basic block. 10 is a separate basic block, then 11 and 12 is a separate basic block, then you have 14, 15, 16, each one their own separate basic blocks, okay? And again, if you look at this, the reason that you're doing this is that you need continuous blocks. You can, for example, check what will happen if I put 15 and 16 together. Would that create the same basic block or not? And you will see that it's not, because, for example, depending on the condition of y, sometimes you execute this, but you always execute this. Okay? Yeah. 9 and 13 and 14 together? Why not 13 and 14 together? Well, 13 is really not an instruction, right? So there is no 13 here, actually. Yeah, well, yeah, you could technically say that 13 and 14 are here, and entry point is essentially 13. Yeah, and the exit point is 14. But yeah, I agree. It's kind of like the reason is this is the beginning of the function. That's actually there is something going on here, versus the here is mostly just a syntax. You could have just removed this, but you cannot remove this, right? So that's the difference. So if you remove 13, like the curly bracket from 13, and move it up, doesn't matter really. Nothing changes here. Well, 2 and 3 would be the same, right? So yeah. But yeah, so things like syntaxes, it's really not important. Yeah.
So can you make the whole while loop in its own block? For example, 10 to 12.
10 to 12?
Yeah.
You cannot, because your exit point in this block is 10, right? It's not 12. So you remember that things should have its own entry point and exit point. So there is very possible that you enter 10 and you exit 10 without really executing 11 to 12. Versus the definition of basic block is that if I enter the basic block, I have to go all the way down and then exit. Okay. So 10 and 11 and 12 cannot be at the same time. It's similar to, for example, 5 and 6, if you look at it, right? So 5 and 6 is not part of the same thing, because you can enter the if condition not going through the inside of the if condition, because the condition might be incorrect. Any other questions from this? And then, of course, as I said, I'm just showing you an example at the C level. One could look at this at the assembly level or even the binary, and then the basic block for this would be exactly the same. And you can actually, an interesting thing that you can see is that for a code simple as this, you would see that you actually have 9 different blocks in the system, right? So you can quickly see that how, the number of blocks, just rapidly increase as we move to a more complex system. This is just a simple, sequence of like one if then else's, another if, and one while loop, and that results into 9 different basic blocks. So this is so based on this basic block, we're gonna draw what we call a CFG, or a control flow graph. Control flow graph is a very powerful program representation. The idea of CFG is that you draw these basic blocks and you draw the connection between these basic blocks in order to show you the sequence of different paths that the program has. Essentially, by CFG, you can describe the common path that the program has. And I already told you that why paths are important for us. For both our static analysis and dynamic analysis, we need to be able to extract the path and check this path against some known techniques. So, for example, if we want to do some form of control flow integrity, I need to know whether this path is a legitimate path or is it a new path that I need to detect and protect. The reason that we call it a graph, because we essentially, represent this as a graph, which essentially in this graph, this graph G, nodes are your basic blocks. Okay, so for example, in this particular previous case, you will have 9 different nodes, and then the connection, the transition between this basic blocks becomes your edges. Okay, so for example, from 1 you go to 2, so there will be an edge between 1 and 2, and so on and so forth. So this is how we can actually kind of create an edge. When there is an edge between 2 basic blocks, it means that from one basic block you can jump to another basic block. Okay, so this is usually what we represent. We represent it as G, N, and E, which N is the number of nodes and E number of edges. A classic way of showing, showing a common graph. So this is kind of like, let me see if I say anything here that I didn't say. So yeah, as I said, edge essentially indicate the flow of instructions, right? So you can kind of follow the program order by following the edges. And then when you see an edge, it means that the control has been transferred from one basic block to another basic block. And then essentially, the program usually starts from an start point. So any program has like a particular start point, and any program has a particular endpoint. There might be multiple endpoints. There's no reason that there's only one, but once it ends, right? So that's usually what we do. So going back to this examples that we have, this is the basic block kind of things. You can easily now see that how this becomes much more understandable to human eye when we are seeing something like this, right? So, your program starts from the top, it goes through this kind of sequence of initialization of the power and z, and then the if condition. If the condition is true, then we run basic log 2. If it's false, we run basic log 3. Then both of them kind of merge, regardless of whether we take the if or the else path. Both of them comes to 4. Then from 4, we go to the while loop, and this is where we're going to have this back edge, right? So from 5, we go to 6, and from 6, we can come back to 5. And then from that, we go to 7. From 7, we either go directly to 9, and from 7, we either go to 8, and then 9, and so on and so forth. So this is kind of very clear that these are the common path. And as I said, the important thing about this is this now gives you the possible transition. So again, going back to defending against something like a control flow, you will see that from 1, you cannot jump to 5. You cannot jump to any other arbitrary location in the memory. The only thing that you can jump from 1 is either 2 or 3. So if I see I'm jumping to 2 or 3, I'm happy, system is working correctly. But if it's jumping to anywhere else other than 2 and 3, that's an indication of this is an attack, okay? And again, if you really want to show it in terms of graph, if you remember, I told you that we call this a CFG, for example, in this case, let's call it power, which because the name of the function. The nodes are the start nodes. We usually, by the way, add the start and end nodes to the graph to kind of make it more visible. Then we have 1, 2, 3, 4, 9 up to the end. And then our edges are essentially all the edges. So we have one edge from start to 1, one edge from 1 to 2, from 1 to 3, from 2 to 4, 3 to 4, 4 to 5, 5 to 6, 5 to 7, and 7 to 8, 7 to 9, and 9 to n. Right, so these are kind of like the potential ways of having different edges in our system, right? And again, usually instead of like showing this entire, and by the way, there should be one here that I think it's not being shown here. So there is 1 to 5 to 7 as well that you might have as well, that I think here for some reason is not being shown, because you can just skip 6 and then jump to 7 directly, right? So there is a 5 to 7 that for some reason I'm not showing it here. Anyway, so usually the way to show this is we are using it like this. So we rarely kind of show it like that. We usually show it by just the basic block. So we start from 1 to 2, from 1 either go to 2 or 3, and then 4, then 5. From 5, as I said, we can either skip to 7 or go to 6, and from 6 we can only come back to 5, and so on and so forth, right? So that's kind of the idea. And yeah, this is the exact same thing that I'm showing you here. Any questions? If you're really interested in the assembly version, this is how the assembly version looks. So there will be, so this is, how many of you have seen, I've used IDA or IDA Pro, the tool? None of you, okay. So yeah, if you're like, looking to binary analysis, this is like one of them that we use. So this is actually extracted from IDA Pro. So you see that, for example, at the beginning, as I said, there's a bunch of push and moves and so on in order to create the space for the local variables. Then at some point, we're gonna do some checks, some comparison, and some jumps. This is, by the way, x86. Assembly language. How many of you are familiar with x86 assembly language? A few of you. Okay. So yeah, I mean, you don't need to, but we just, and then of course here is where that's the first kind of if then else is, and as you can see, you usually have this location kind of labels. And then from there you go to your 4. So this is your 4, this is your 5, this is your kind of 6, this is your 7. And so on and so forth. I think this is your 7. No, sorry, I think this is your 7. Anyway, I think this is your 7. Because you can jump over it. And then this is basically what you're gonna get from your code. Okay? Questions? We're good? Yeah, this could be a good practice for you to kind of like, if you're curious about how the assembly language of the assembly representation of the same code works, this is how it works. All right, so we have also the notion of path. So as I said, this is the traverse between one basic block to another basic block to another basic block. So we can kind of like have, the general path from start to end. We can also have subpath, which means that, we, from one specific basic block to another basic block, we can kind of define it. So usually we, as I said, we can define path as, a list of, a vector of edges from E where K is more than 0. So as I said, path doesn't necessarily means the entire program flow path. It could be, for example, from one basic block to another and then another. That's also considered a path. And then the reason that path is important for us is that because we want to make sure that we can see all the path and we can check all the path and make sure that, all the paths are the observed paths in the system. And then, the rest is a little bit of graph theory that I'm not going to go through, but you can, for example, count the number of possible paths in a program, give a number of edges, and so on and so forth. So if you're curious about these things, you can always take a look at them. Okay. And then, as I said, the last thing is like the difference between complete path and subpath. As I said, the definition of path could be like anything that starts from start to finish. It could be also kind of like, a subpath could be, anything that starts from one edge to another edge. Okay, so any sort of subset of a complete path would be a subpath. Again, here are the examples of regular subpath. And then, for example, something like this is not a valid path. So cannot say 1, 2, 3, 4, because if there is no valid edge between the two nodes, then this is not part of your path. All right. Let's have a quick break here, and then we're going to come back and follow this. All right, let's continue. All right, so you can have paths and subpaths, as I said. The important thing is we do this all to get to this point, and that's the notion of feasibility, okay? So feasibility means that is it possible to have a particular path, which means that is it possible to go from one basic block to another basic block, or from one sequence of basic blocks to another sequence of basic blocks, okay? The reason for this is we want to be able to detect, for example, whether this is an unauthorized jump. And by the way, as I said before, this is not just for security. The notion of path and control flow and control flow graph is extensively used in software engineering and debugging as well, because in software engineering, you also want to make sure that you can reach to a particular part of the program, or if you cannot reach, how can you reach to that particular part of the program, and so on and so forth, okay? So in other words, we consider a path through CFG feasible if there exists at least one test case, there is one input that cause to observe all the nodes within that path, okay? So to give you an example, a feasible path is start 1, 2, 4, 5, 6, 7, 6, 5, 6, 5, 7, 8, 9, end. Right, so this is a possible path, and one can find an input that kind of satisfies this path, right? But an infeasible path, of course, is doing start 1, 3, 5, like 5, 4, 5, 6, 5, 7. Let me see, 1, 3, 4, 5, 6, 5, 7, 8, 9, 10. So that would be another that would be an impossible path to go, because you cannot find an input that both satisfy this part, that y, for example, is equal less than 0, and power is negative, right? So there's not possible that, any particular inputs kind of satisfy both of them, right? So there are things that cause, a path to be satisfiable, or depending on input, the path could be unsatisfiable, right? Another one would be 1, 2, 4, 5, 7, 9. And again, here you either your y is equal to less than 0 or more than 0. If it is, then it follows a specific pattern that it doesn't. If it's not, then it doesn't. In other words, you have to understand the fact that depending on the input and depending on the control flow, not all the paths are feasible paths. Okay? And that's why important for when you use control flow integrity. Okay? And then, of course, you want to count the number of paths, and this is something that we might ask you to do in future. And then again, the problem with number of paths is kind of like it's multiplicative, right? So if you add more nodes to the graph, then you kind of grows exponentially with the number of paths. So that's usually the problem with all these static and dynamic based these mechanisms. All right. So to recap, we are trying to find bugs, okay? And the reason that we are interested in bugs is because we want to defend against memory corruption. But as I said, this bugs could be also be found for other purposes, such as software engineering. We are looking at binary analysis, and we start talking about static tools. The idea of static tools is that we kind of go through the program line by line, trying to kind of extract some rules and then find some specific patterns. An example of this is like, for example, creating the control flow graph, counting the number of paths, or checking the feasibility of path, right? The reason that we create control flow graph, as I said, was that you want to be able to kind of create an abstraction that is understandable by human, right? So otherwise you cannot really parse through a code that you're not really understanding. So the reason that we create this kind of abstraction, this kind of man-made abstraction, was kind of just understanding this. The problem, as I said, is the scalability or the coverage issue, because you can quickly see that, even for a simple program, the number of different basic blocks, grows significantly. You have like 9 different basic blocks. And if you actually start counting this number of paths, you will see that this number of paths is also a huge amount, right? And unfortunately, it's kind of multiplicative, which means that if I add more and more of these nodes, the number of paths kind of multiply by that many, right? So if I, like all the paths that I find, if I add one node at the end, essentially I'm kind of like adding, like whatever I have times the number of more paths that I'm adding here, right? So it's very quickly kind of grows significantly. Okay? Yeah.
So does that mean, for the second bullet point, in the previous slide, how about finding every path
Mm-hmm.
instead of every single instruction?
So you can find like finding all the paths is hard, but finding one single instruction, whether that single instruction has been executed or not, much easier problem, right? Because you can just follow the path and see whether that single instruction has been executed.
Right. It's just like the wording confuses me a little bit, because the first bullet point mentioned instruction, and then the second bullet point also mentioned instruction.
No. So the difference is I can check whether or not an particular instruction is problematic, just one instruction. But every single instruction means that now I need to go through all the path in order to find this, right? So the problematic part is if I want to check every instruction, then this means this is equivalent of finding all the paths in my program, which is very time consuming. It's still doable, but very time consuming. Does that make sense?
Yes.
So yeah, this is exactly what I'm saying here, showing here that finding all the paths is a hard problem. There are billions of instructions, but we need to find as much as we can. So it's not like, oh, we don't do this. We actually do this in many systems. And as I said, dynamic tools has its own benefits, because essentially you can check individual instructions as they go through. So how do we do that? We use various different tools. One of them is called Intel Pin Tools. If you're interested to learn more about pin tools, you can actually check, the truthers. I'm gonna very quickly go over it. I'm not gonna go through the details of it. But generally, if you're kind of curious about this dynamic binary analysis tools, this is an example of it. Initially, I was planning to kind of like define this the computer assignment based on pin tools, but pin tools has its own kind of challenges. It might take a little bit of time for you to kind of learn how to use it. So I decided eventually not to do it. But to give you kind of like in a nutshell how pin tool works, pin tool is this dynamic instrumentation tool, which means that as your program runs, it collects traces. Okay. The way it works is it's actually kind of transferring this kind of piece of code. So this is just a regular assembly code in x86. What it does is that it gives you this very strong capability that you can add arbitrary code, in this case, assembly language code, in between your instructions. And you can decide where you want to insert this, okay? For example, the famous one is, for example, you want to count the number of instructions. How many instructions am I executing in this system? Dynamic number of instructions. Essentially, what it does is that you kind of count or increment a counter between every two instructions, right? So if I insert a counter increment between any two instructions that I execute, essentially I just can count how many instructions have I executed, right? And you can do more sophisticated things with pin tools. Again, if you're interested, you can go and take a look at it. So there are different usage of pin tool. You can do program analysis, error detection. You can do architectural studies. So it's not just telling you about the ISA. It can also tell you about things such as the number of cache misses, branch misprediction, stuff like that. You can instrument your source code, so you can actually insert this at C level. You can even do it at the static binary level, or you can even do it dynamically during the execution. So all these three things are possible with pin tool. In other words, this is what we call just-in-time instrumentation, or JIT. Right? Just-in-time is just right before the code is executed, you're adding this instrumentation. There's no need to recompile your code. There's no need to kind of discover your code and all those things. Everything just happens dynamically during the execution. It doesn't stand for anything, as these guys are suggesting, and it works on multiple platforms. You can actually run it on your Linux and Windows or MacBooks. So I definitely recommend you to take a look at it and use it if you want to kind of give you some insight of how a binary analysis tool works. There are a couple of examples that you can do. For example, let me see if there are examples here. Yeah, so this is, for example, how you would run it. So you kind of write this code. This is, for example, inscount.dll if you're using the Windows version, or generally this inscount is a .cpp file. It's the file that you're going to use in order to insert the code that you want. Then what you would do is that this is your target binary. Okay, this is the program that you want to profile. For example, this power function that I described, you can kind of compile this into power.exe, and then you can, for example, wants to see how many instructions this power.exe has. So you kind of feed it into this pin tool with this DLL, and then this would be your binary that you want to test. And then, of course, you might have some inputs to your binary that you want to test as well. And then this is generally how the application would work. So essentially, this is kind of like, you don't need to understand all of these, but this is generally worked with your kernel in order to kind of like, get your application process and a whole bunch of things that are going on in parallel with it, that basically kind of gets the data from your binary and then use it with this pin tool. So this pin tool essentially launch another tool that kind of do all these things for you, which let's actually skip this because it's not that much relevant to your and then this is kind of like what the inscount does. So essentially, as I said, this is a simple thing that it does is just counting the number of instructions. Okay. There is a particular format for functions that you write for pintool. All of them has this main file that has this instrumentation function and fini function and all those things. But really what you do is that you're defining this function that you want. And again, the function that you do is just a simple I count. So you just count the number of instructions in this particular case. Everything else is kind of like just gonna being taken care of by pintool itself. So for example, this is how it's going to be translated, okay? So it's going to add this I count in between of every single instruction that you have in your code, okay? So in other words, kind of if you have your binary or your assembly code here, it's kind of interleave this kind of I counts every single time that you're running an instruction, okay? That's what it does. And that's how you're going to actually get the information. Another interesting that it has this analysis engine, which kind of runs at the end. So if you actually look into this fini function, this final function is kind of whatever you collect during your instrumentation, you can actually do the test at this fini function. So they call it analysis section of the code. So your instrumentation happens when the instruction is running, and then the analysis can happen at the end of this execution. There are some examples that I'm going to skip. This is basically very similar to the same way that I showed you a control flow graph. So for example, if you have a control flow graph like this, like the basic block, what you can do is that you can, first of all, you can get the trace. You can also create the basic blocks. You can know when the jump happens and when you exit a basic block and all those things. So basically, pintool can be used as a binary analysis tool to give you all this information. And then again, this is another example of doing a little bit more sophisticated instruction counts. Again, if you're interested, please go and take a look. It can even support multiple cores and multiple threads. So if you, for example, have a bunch of different cores that are running at the same time, Pin can also kind of take a look here and track all of them at the same time. Yeah, all right. So just a general introduction of what a tool like this can do. These are like very powerful tools. Another tool that you probably want to take a look at is called Anger, A-N-G-R. This is a Python-based code, and what it does is kind of also doing like this binary analysis, static analysis. The goal here was to give you just an overview of tools that exist. And then in your computer assignments, you're going to actually develop your own tool, like your own bare bone basic tool that can do something similar to pintool, but not as, of course, sophisticated. It's just a very simplified version of that. All right. So as I said, the challenges in both a static and dynamic analysis tool is the coverage, because there are potentially many different possibilities, many different input combinations. And regardless of what you do or what tools you do use, this coverage is a big problem that you need to solve. In order to fix this problem, we usually use this kind of analysis methodology called symbolic execution. Okay, so what is symbolic execution? How many of you have heard about symbolic execution before? Okay, so the idea is this, that, okay, so if I have like something like this, okay, that if I have like a control flow graph like this, all right, I have many different paths, right? So I can start from here, go here, from here, I might go here, I might go here, and so on and so forth, right? And I told you that, this number of paths is growing significantly, okay? The idea of symbolic execution is, let's run this symbolically, which means that for each of these kind of conditions, we create a parameter, like let's say alpha, and then condition upon this alpha, then we move forward. So we create this giant expression that's saying that, let me see if I have, yeah, a giant expression that based on this, the conditions, we're going to decide what to do. So let me actually give you an example. This is much easier to understand. let's, for example, say this is your code, okay? You have X, Y, and Z. These are your local parameters. Then you have a series of if-then else's, okay? So for example, if A is true, then X is equal to -2, if B is less than 5, and if A and C is something, something, and then we're gonna assert something at the end, okay? So this is your kind of control flow. If you actually kind of start looking at this, you will see that based on the condition of A, you're gonna either run this or you're gonna skip this and run this. And then again, based on this condition and these two conditions, you're gonna either run this or you're gonna skip and run this, and so on and so forth. So the idea of symbolic execution is, let's actually create a symbolic or otherwise kind of like a variable that shows the condition in terms of a variable, okay? So in this case, A is essentially my alpha, and then in this case, it's just A. So it's if A is bigger than 0 or otherwise alpha is bigger than 0, then we're gonna either do this, or we're gonna, if this is false, we're gonna then check another condition. In this condition, we make B as a symbolic variable beta, and then again continue with this. So for example, now we have alpha, the knot of alpha, and with gamma, which is the symbolic version of C, and so on and so forth. And as you can see, eventually we're going to get different values. So for example, Y is equal to 1 and Z is equal to 2 if alpha is false, beta is less than 5, and knot of alpha and with gamma is true. So if all these conditions are true, then you're going to get this value, right? So in other words, instead of actually trying to go through the different conditions, I'm trying to create an expression of different symbolic variables and then trying to basically solve this condition. So solving this condition will give me this value, okay? So I'm going to get this symbolic conditions of variables, and I'm going to try to find a satisfiable expression that satisfies this condition. If I can't find one, then it means that this is a valid path. If I cannot find anything here, then this means that this is an invalid path, okay? How do we solve that? We're going to use SAT solvers. So you probably have seen this things like this before, that, you know, we have a logic formula of, you know, various different variables and an OR together. This is what we call a SAT problem, and you probably have heard about the SAT solver. How do we find X and Y's, you know, X1 to X3 in order to find a set of zeros and ones that satisfy this condition? If you can find one, for example, in this particular case, if X1 is true, X2 is false, and X3 is true, then this condition is satisfied. And this exactly means that, for example, if I can find a satisfiable argument for this, it means that this path is a possible path. So in other words, Z equal to is a possible outcome of the system. All right. How many of you have heard about SAT problem? Some of you, hopefully. How many of you remember what is a SAT problem? Or how do we solve a SAT problem? How do we solve a SAT problem?
I think satisfiability is actually complete, so you have to try them. Or
Yeah.
Try them all.
How do you try them?
You like assign an arbitrary value to all the variables like true or false, and then value the expression, see if it's true or false, and show them.
Any algorithm do you follow, or is it just brute force?
If I remember, I don't know if you can do better than brute force.
Okay. So it's something like greedy search you can do, breadth first you can do. There are various different ways that you can try to.
General satisfiability, like arbitrary.
Yeah. So the overall idea is that there is no known algorithm for this, so because this is an NP-hard problem, right? So what you do is that you start to kind of make some guesses, and then you're trying to improve your guesses, okay? That's why you need a SAT solver. There are like programs that can do this very quickly for you, all right? So the bottom line is that I did all this in order to kind of avoid the fact that I need to kind of go through all the paths. What I did is that I can quickly create these conditions, okay? I can just quickly go through this path and go through the leaf of my tree in order to achieve these conditions, okay? Now the question is, can I satisfy this condition? In other words, can I find values for A, B, and C? Remember, A, B, and C are my inputs, okay? Can I find a value for A, a value for B, a value for C, such that this path becomes a valid path? If I can find that, this means that this is a feasible path. If it's a feasible path, then there's nothing wrong with it, right? There's no bug. If it's not a feasible path, then this is a bug. In order to know what's feasible or what not feasible, I'm creating these conditions based on, instead of using the actual inputs, I use the symbolized version of the inputs. I create propagate them through these conditions. I create these conditions eventually, and now I need to find a satisfiable expression for each one individually. So I try to solve this, then I try to solve this, then I try to solve this, and so on and so forth. Okay, that's the whole idea of symbolic execution. Questions? Does that make sense? Good. All right. So symbolic execution solved a little bit, but it still has its own problems because, again, finding these expressions is not as easy that you think it is, because again, you still kind of needs to go through this true or false statements every time, and this is not necessarily something that you want to be able to do for a complex program. And so you kind of like have some of this path explosion and complexity slightly better than just going through like concrete examples. Okay, what you can do in order to kind of fix the issue is doing what we call concolic execution, which is a combination of having concrete implementation and symbolic. In other words, in this example, basically what I told you is that all of your inputs can be kind of substituted with a symbolized expression, okay? But what I can do is that, for example, I can say that A remains A. I use a concrete value for A, which means that, for example, I say A is equal to 1. And then I solve the symbolic expression for beta and gamma, okay? The reason for this is that then this kind of solves lots of these. So for example, half of this tree will be gone. Either we're going to do it this way or I'm going to go this way because I know the concrete value of A. The downside is that now I need to repeat this for every A, right? So I need to do A0, A1, A2, A3. But if somehow I know that there is a concrete value, so I no longer need to symbolize this, I can do this concolic execution, which means that some of my variables are concrete, which means that I know exactly what their values are. Some of them are symbolic, which means that I don't make any assumption about their values. I just create the expression, and then I try to use the SAT solver in order to find the inputs for that. Okay, that's kind of like the idea of a concrete execution. That's kind of like trying to kind of find a balance between the search space and your SAT solver. Okay, if you concrete everything, you're going back to square one, which means that you need to run all the inputs. If you do everything in symbolic, then you need to kind of like have a gigantic SAT expression that you need to solve. So somewhere in between is like you concretize some of the inputs and you create a symbolic execution for some other, and together then you can solve what we call a concolic execution. Okay. All right, so to quickly recap of the things that we discussed is that we're trying to interact with memory, and unfortunately interaction with memory causes corruptions. The reason for this is we are using unsafe code and data, and the attacker can use various different ways of corrupting our memory. We show that how this corruption can lead into like meaningful attacks. And then we start kind of defending against this. The big thing that we wanted to defend against was finding instances where the code can be corrupted, okay? And then we start defining, using static tools and dynamic tools. We show you how we can use control flow graph, and how from control flow graph we can use path, and then from path how we can create the notion of feasibility, right? Then we said that the problem with the feasibility is that you need to kind of traverse through all these different paths. So you either use the sophisticated tools like pin tools, or you use some form of notion of a better way of analyzing this using mathematical expression, which means that instead of trying to say that, okay, my input is 0, 1, and 2, you say that my input is alpha, beta, and gamma. Let's actually go through the mathematical expression based on not assuming what the concrete values are, create the expressions. Now I have the final expression. Now I know a fast way of solving this expression because I have a SAT solver that very quickly can go through this example. So it's much faster than going through all these paths one by one, rather than just creating the expression for all of them together and then solving that. Okay, that's why you want to use something like a symbolic execution. And as I said, one way of optimizing a symbolic execution is use concrete and symbolic together, which we call it concolic, which means that instead of making expression for everything, let's say some of them we know and some of them are expressions. And together we're going to then have a SAT problem that some of them already know what are their values, some of them we don't, and we try to solve this problem, right? So it's much more manageable problem because, for example, let's say if early on in your tree you can kind of concretize things, then most of your tree is gone because like half of the tree is kind of false, for example. If your value is true, then you don't need to kind of go through the false route, okay? So that's kind of like it for the design of memory for options and detection of that. Okay. So yeah, control flow integrity. I think I talked about that. There's a whole bunch of other types of corruptions that I didn't talk about: integer overflow, heap spraying, use after free. I kind of talk about this one. Format string vulnerabilities. These are all just ways of corrupting your memory. As I said, there are many of these exist in your system. All right. So I think that's it for, and then generally, unfortunately, this is kind of like a loop of vulnerabilities, fix vulnerabilities, fix vulnerabilities, and so on. So this is, as I said, this is a problem that we kind of started like many years ago, and we're still dealing with issues because, you know, we make stack unexecutable, then, you know, there's ROP attacks. We fix ROP attacks, there's another and another. So this is not going to be going away anytime soon, unfortunately. Questions? All right, so we have a little bit of time. Let me actually go over this assignment very quickly. All right, so here's what we want from you to do, okay? So we are giving you two programs. One of them is a simpler program, and the other one is a little bit more complicated. You can actually click on this link, and you will find that. I want you to write a Python code that does this thing that we did in the class automatically. So I want you to kind of create this table, okay, that's for the given C++ program on those two files, can create a table like this. How does the table look like doesn't matter, but it has to have like kind of 4 columns. It shows us the number of basic blocks, the lines that include in each basic block, the entry point, and the exit point of each basic block. Okay, so you need to kind of like create a program that takes this dot. So you treat this kind of program as a text file, right? And you kind of parse through line by line, and then decide whether that line belongs to one basic block or creates a new basic block, right? And then you go through every line of the code until to reach to the end. And at the end, you should have your entire table populated, okay? So there are various different things that you need to think about. For example, what constitutes a new basic block? And the hint here is you have to think about control flow instructions, right? What creates a new basic block is a control flow instruction. So you have to understand what is a control flow instruction and how do you parse that. And then when you have a control flow instructions, how do you going to create a new basic block? And how do you know that that basic block ends, right? So these are kind of, you need to think about your data structure, how you're going to create your data structures, and then how you actually kind of append things to that kind of data structure that you have for every single one of them. One thing that you can make your life easier is you don't need to be exhaustive in terms of all the control flows. You can just assume that the control flow you see in these two files are the control flows that you see in a regular program. Yeah.
I was curious about how we should parse if statements without following else's, considering that if we're using the sample, there's no open bracket,
Mm-hmm.
and so you can't really know the exact end. Is it just next statement because it's C, or do you have to like have a special case for it?
So the question is, how do we know whether if a statement has like how many lines? It's like a C syntax, right? So either you have a curly bracket, which means that everything within that curly brackets are part of your if. If there is no curly brackets, just the immediate line is your if segment and nothing else.
So we're essentially just writing like Alexa for C, and then
Yes, yes, you kind of like you write some form of a lecture, but simple one, right? So it's not, for example, you can assume like if it makes your life easier, you can assume that all your if statements has a curly bracket because you have your C code, so you can just add it if you want to. Yeah.
Sorry, that's,
Don't worry, take your time. Any other questions? And then you repeat it for both of these files, okay? And then you create a Jupyter notebook like the ones that you created before, that you show your code, you kind of show the output of your tables for each one, and then you have some description of how your code works, and then you submit that, okay? I'm not gonna test it in some unknown program. Just make sure that you just test it on these two programs. Yeah.
Are you lenient on whether we have like an exit point be like a bracket or the line after it? And it kind of goes into what we discussed.
Like this, like whether 13, for example, is part of 12 or not.
Yeah.
Yeah, as long as it makes sense, that's fine. What we can do is that I can go over the text and make sure that it's consistent with what we discussed in the class, so that because you only need to test on those two samples. Does that make sense? Any other questions? And then only for the main function, right? So by the way, you can do this for assembly version. Assembly version is actually slightly easier because it gets rid of all these brackets and this kind of like, parsing through the complicated code. But that means that you have to understand the assembly language and then kind of like parse it through that. But if you do the assembly version, just make sure that you're just only do it for the main function, right? Because if you compile this code and disassemble it, you will see that there will be lots of things, other things that will be added to your binary, okay? We're not interested in the basic blocks of that. We're just interested in the basic block of your main function, okay? So it just makes your life easy, yeah.
Must the assembly be x86, 64 or can
It can be any language that you want. So if you want to, for example, like use a compiler to do RISC-V and then do it, that's fine as well. Just make sure that you show the assembly code in your Jupyter notebook as well. I mean, I'm assuming that you're using an x86 machine. That's why if you compile it, it will create an assembly. But if you need to use a cross compiler, if you're using something else.
So we can like interpret an ARM assembly output?
I mean, again, if you use an ARM compiler, cross compile it, and then disassemble it, yes, you can. You're given a C code, so you have to compile it yourself. But yeah, whatever language that you want. Of course, a RISC-based language probably easier than x86, especially if you're familiar with ARM or RISC-V or so on. Any other questions? Yeah. How do you put that in Jupyter Notebook? So you compile your code, right? And you get a file. You can just you can treat this as a .text file, right? So you can just read it as a text file in your Jupyter Notebook, right? Or you can just copy and paste it and then read it. There are many ways. You can read a text file, right? So you can import a text file in your notebook, and that's what you You don't want to compile it there. I mean, you can compile it there, I think, using Python. But the easier thing is that you just read. I mean, if you're treating it as a C code, then you just read it as a text file. If you want to use the assembly version, compile it, disassemble it offline, you have the assembly version, then import that assembly version.
It's fine.
You read it as a text file, exactly. That's how the compiler works too. But of course, you can actually create a dynamic tool that it runs, everything, but that would be much, much more complicated thing to do. So I don't recommend. Any final questions? We're good? All right. Thank you, guys.